Welcome everyone to our Infinity Pulse presentation. My name is Reginald Pangindian and I am from Team MedGen. And we'd like to thank you guys, we'd like to thank the professors, judges, students, and fellow colleagues for all your time here.
My name is Ashley Bowens. I'm also a member of MedGen. I'd like to take the time to introduce or get my team to introduce themselves. We've been working with them closely over the past year, so you guys want to.
I'm current semester's team manager, Dan Berry.
I'm Logan Hall.
I'm Justin Masters.
And I'm Brendan Tech.
Okay, so quickly going over the agenda for today. As the judges can see by your marking schemes, we followed in order the section that you guys have been marking us on. For those of you that don't have marking schemes, as you can see, we'll be going over the device description, functional tests, amplifier design, internal calibration signal, the readouts, simple quality upgrades, significant quality upgrades, bonus marks, miscellaneous marks, the overall project demonstration, and the conclusion. Myself and Reggie are going to be presenting section A, which is our device description.
All right, for question one, from the clinical and biomedical perspective, it was first developed as non-invasive blood pressure using a sphygmomanometer, and from there it evolved into invasive blood pressure. Several advantages of this is that it provides continuous blood pressure measurement with greater accuracy and real-time measurements. It also avoids the trauma of repeated cuff inflation to the patient, and you can administer medication through the transducer as well. Disadvantages is that it must be inserted into a patient and cannot be attached for extended periods of time without look over, and it increases the chance for infection. Question two is the clinical and biomedical perspective of intended application functions. And as I said before, it provides real-time blood pressure measurement, and also it provides a waveform of pressure over time. You can also administer medication directly into the patient while continuously monitoring, and any changes can be immediately detected through any alarm settings that the clinician may put in, and is mainly used in ICU and surgery.
Okay, so for the clinical and biomedical perspective of the values of IBP, as Reggie said, it provides continuous blood pressure monitoring. That's very useful in patients who are likely to display sudden changes in blood pressure, so anyone who's had vascular surgery or is getting vascular surgery. It's also important in patients who require close control for blood pressure, so with a head injury or head trauma, where a sudden change in blood pressure can be crucial for patient health. It's IBP techniques. It allows for the accurate blood pressure measurements for those who have very low blood pressure, so patients who are shocked, who have experienced a sudden trauma, their blood pressure drops immediately. IBP is very good and accurate with low readings, whereas IBP is not, non-invasive. It also, as Reggie said, patient comfort. So if you're non-invasive, you have a cuff that is inflating constantly, and it can be a nuisance. It can be uncomfortable to a patient who may already be upset, angry, they just come into the trauma. So the invasive one is a line that goes in the patient, and it's there permanently. You don't have to have the constant inflations from the cuffs. I'd now like to bring up my teammates Jesse and Logan to present the section B, which is the functional test.
We'll be going over the functional tests of our BP amplifier. The first one is the biomedical perspective of our gain function. Ours is a variable scale gain. As we change it, we can jump between the 30, 120, and 300. This can be seen in the schematic here. So you choose here, the gain will change. The other main one is our zero calibration. This is also able to be set every time you change it. It is located up here. It is on the faceplate. So before you hook up a new patient, you will set it back to zero, so 0 atmospheric pressure, to allow a very accurate reading.
So question 5 is the clinical perspective, gain and zero calibration. The purpose of the gain is to manipulate the size of the waveform without distorting the original signal and keeping the waveform faithful. The gain can be adjusted by the knob on the faceplate. The zero calibration opens up to the atmospheric pressure, not allowing any offset which would be present and as such needs to be before hooking up to the patient. The next one is question 7, the biomedical perspective, functional controls and indicators. First step is to turn on the device. Ensure that the display switch is on IBP and not ECG. Adjust to the lowest setting of 30. Input a static signal of 0 and do a zero calibration adjust to align them. In order to get the atmosphere 0, it is then ready to be hooked up to the patient.
Where ours are on our device is, this is our zero cal knob, so we can change it to allow wherever your zero cal is at that time. And our gain control is right beside it. This is our scale gain, so our 30, 120, and 300 scale gain on our 8620 amplifier. We'd now like to re-invite up Ashley and Reginald to talk about our amplifier design.
All right, so the chart that you see up on the screen right now is the AMI standards that we found for IBP. You can see we have pressure range, overpressure without damage, the linearity and hysteresis, the maximum balance. As for the risk current out of 120 volts, above the defibrillator withstand, we were not able to test the defibrillator withstand or maintain the risk current at 120 volts due to resource limitations and time management. Obviously, they are important for patient safety too, for medical devices to follow these standards, but like I said, with our project, it's not intended for medical use, so we didn't.
All right, so question 10 is the biomedical perspective of the technical specifications when looking for an amplifier. We chose the 8620 because it has a high slew rate, open loop gain, CMRR, drift, noise, high input impedance, and low input output impedance, because we needed a waveform that could be consistent throughout the entire circuit.
Okay, so for the biomedical perspective on slew rate and response time, slew rate is defined as the maximum rate of change of the output voltage over a period of time. With IBP, it is important to use such components that increase the slew rate as much as possible, seeing that IBP relies on real-time monitoring for blood pressure. So if you have a slow slew rate, it means that the output waveform or data is going to be delayed. You're not going to have the same signal coming out of the patient that's actually happening. So the patient can have something go wrong, 30 seconds later you have a wave come out, it's not useful, it's delayed time, and for patient safety, it's not useful. The image that I have up there just shows you have the input wave on the top, so that's what's out slew rate. The bottom is the output wave, which is coming out on the display screen. So you want to have it as close to the input as possible to decrease the delay, which I talked about.
Question 12, from the biomedical perspective, our gain is a linear dynamic range, which means it will not affect the actual measurement, and only the size will be. It has to be in compliance with the AMI IBP standard, because if you adjust the gain and it actually affects the signal, you will have unfaithful results and therefore misdiagnosis of the patient. You can treat them for something completely different than what's going on. And as shown before, Logan showed you where the adjustable knob is. There are 3 settings for our adjustable gain. And from there.
So the biomedical perspective on the common mode rejection. This is needed because without it, the noise of the signal would be amplified along with the signal as well. The whole point of common mode rejection is to reduce the noise and make the signal as clear as possible. So on the top, you can see a signal there without a common mode rejection ratio, and on the bottom, it's one with it. So you can see how much noise is coming out of the signal. That's important for patient use. Obviously, you don't want a signal coming out, a clinician looking at it saying, oh, we've got this going on, when it's actually just noise being picked up in the atmosphere.
Question 14, frequent response. The device has to actually meet the frequency of the signal itself, and it cannot be under the frequency rate of the signal. What this means is that any signal that is above 50 hertz can be considered noise and non-useful information to the clinician, and under 50 hertz can be considered useful to the clinician and considered biosignal.
So now we have the clinical perspective of waveform reproduction. As I mentioned earlier, the clinician is going to be looking at the waveform, so anything coming out of the machine and our patient, the clinician is going to look at it and take it as a diagnosis. It can be noise interference, you could have problems with the machine, but the clinician's not going to think of that. They're going to think, okay, I've got this kind of signal coming out, this is the problem, they're going to treat the patient. Could be a misdiagnosis due to noise or calibration problems with the machine, so this is why it's important to have faithful reproduction with the signal. I'd now like to bring up Dan and Brendan for section D on internal calibrations.
So we will be speaking of the internal calibration signal. First off, the internal biomedical perspective of the internal calibration. We've included several calibration points through potentiometers for the instrumentation amplifier, gain select, the diastolic peak detector, which involves an inverter, and the DC offset. Systolic peak detector and the mean arterial pressure is actually calibrated through the original software. The troubleshooting aids, we've selected several other points. Test points for where the signal comes in, gain is supplied, or signal is outputting. LEDs for power being in the boards, or pulses coming from any signals changing. Connectivity and Molex connectors are one of the main things. We can do connectivity check on several points in the circuits. And the Molex connectors we've selected so that we're allowed to able to hot swap the circuits while it's running.
Okay, for question 18, the biomedical perspective of calibrating the waveform. The calibration has produced a rapid rise time, a noiseless flat peak, and a rapid decay. This could be caused to too much gain within the, it would be caused a flat noise peak because there's too much positive voltage saturation in the rapid decay, which indicates high voltage gain. Okay, clinical perspective of internal calibration. This is used for clinicians so they have the ability to compare a known true signal to the signal on the device. This is so they don't need technologists to come in to calibrate the device when it needs to be calibrated.
And now I'd like to pass back to Jesse and Logan to do the Section 8 readout.
Okay. Question 20, the clinical and biomedical perspective verification of values. So on our LCD display shows the heart rate, the systolic, diastolic, mean arterial pressure, and configures through the Arduino programming code and
Where we read all these readouts would actually be on this screen up here. When it's powered up and activated, there is that heart rate, systolic, diastolic, and map number readout that is easily readable, as well as the waveform appearing on a larger screen. The internal calibrations for this is just the LCD screen. As when there's nothing in there, it'll just be a dash line showing there is no input. When there is an input, numbers will appear, and you can accurately see the same thing on the output signal wave on the other screen in the oscilloscope. This allows for faithful and accurate numbers.
So for question 23, the clinical and biomedical perspective, the systolic, diastolic, and mean pressure. So systolic is the first number or the top number in your blood pressure reading. It's highest level of your blood pressure when it reaches your heartbeat. The diastolic is your second number or the bottom number on your blood pressure reading. It reaches your blood pressure readings when the lowest pressure at the transducer site. The mean arterial pressure is derived from the patient's systolic blood pressure and diastolic blood pressure. It's a better indicator of tissue perfusion, and a patient must maintain a mean arterial pressure of 60 millimeters mercury or higher in order to maintain an adequate tissue perfusion.
As I explained before, the readout screen is the smaller screen. It's very bright. It's easily able to change the contrast. It can be seen from any angles, and it continuously monitors our readouts. This allows for, as I said, an easy and accurate reading. We'd now like to pass it back to Dan and Brendan to explain simple quality upgrades.
Okay, so question 25, the biomedical perspective of the circuit board assembly. Our boards are more organized. We use the motherboard to power all of our circuits within our board. We did this so there's less wires, and it's easier to troubleshoot that way. And it also makes it easier, like there'll be less downtime because there'll be less troubleshooting, and also increases the efficiency. Component layout. Okay, we have it so that each boards that are that work with each other are close together, which would eliminate noise because there's less wiring between the two boards. And it's easy to read the boards too because they're all the same. All the inputs and the outputs are all the same parts on the boards.
question 27, the biomedical perspective, there were 3 test points. We've included test points on all the signal in and output of the amplifiers to trace any issues with noise. The power and ground are all quickly placed along the same line so that you can actually just swap out and test if that's the power on the board is causing any shorts. For 27, the service features, we've got removable top so you can get into and service it. The faceplate is interchangeable, and the lowest connectors allow us to do the hot swapping. The biomedical perspective of the quality improvements, we've included a full metal housing around it to act as a type of Faraday cage. We've used isolated matting on the bottom to stop it from shorting or anything like that. 2-stage power switch, so we've got power coming in to allow AC into the power supply itself. We have a faceplate switch to actually allow it to turn on. We've included the onboard monitor for a clinical perspective of actually viewing the signal without having to attach it to a oscilloscope. The backup battery to allow for transportation, and in case of a power failure, it can pick up immediately to the relay contacts. The integrated readout display to do all the numerical values for the heart rate systolic, diastolic, and mean arterial pressure. And we've also included another revision of the keypad 7-segment display, which is on ECG end, but it configures what goes out to the ports.
Okay, for question 30, the biomedical perspective of noise reducing shielding. We use EMI matting, as Dan said, within our box to reduce noise. We also use shield the power supply from home or other circuits to reduce that noise. And as I said before, we also have it so the whole entire box is shielded from the inside. And we have a medical choke on the back of our switch to filter out 60 Hz noise. And the telecom relays filter control, which is for low voltage and signal relays.
And I'd like to pass back to actually Reggie to talk about the significant quality upgrades. And this section will also include our second.
So one of our first upgrades would be the motherboards layout, because it allows for easy board management, less wiring, easy access, and space management. Because we found out from our first year that if we didn't have this, we would have one fun time trying to figure out which board is powered by which wire. And also it allows for consistent test points without each board. As long as they're in the same place, you can just easily take your testing devices and just go through them very easily. And it also only has one power source, so you don't have to worry about anything. If one dies, they all die, and if they all power, they're all powered as well.
Okay, so for another significant upgrade that we had, we did the LCD display, which you can see on our box there, the large screen. It displays the oscilloscope waveform. It does so by the processing is run on the Pi. It's being configured with the Arduino. The Arduino takes in the analog signal as the input. The signal is then sent to the Pi, where it applies the oscilloscope program so that the waveform is displayed. So I'm sure we'll demonstrate that later to you. But it's kind of cool because instead of having to use the oscilloscope to display the waveform, we can have it right on the ECG box. And it's large and clear, so clinicians could be able to see it very easily.
And from here, we'd like to ask the engineers to introduce themselves and present their piece.
Good afternoon, judges. My name is Mark Wanless. I'm the manager of the second year electronic controls for biomedical engineering. Up here today with me, my co-managers, Jay Wilson and Robin Weaver. I'd like to also pay tribute to my other team members, including Devin Clark, Jason Marr, Harold Cassidan, and James Richards, who are not with us today. Just to introduce the addition, essentially what my team has developed is a way to take any signal essentially and portray it onto an oscilloscope screen. In this instance, it's extremely convenient that we're able to portray a IBP signal. I'm now going to pass it on to Robin to discuss our specialty feature.
Alright, so in a clinical setting, it is essential to be able to adjust the waveform up and down on basically on a patient monitor. So, and also it's very important on the technical side that the voltage remains in safe limits between 0 and 5 volts as we have incorporated voltage sensitive components such as the Arduino microcontroller. So to be able to detect that, we've included a DC offset circuit. So first I would like to demonstrate what a terrible signal looks like. So this is a wandering baseline signal. As you can tell, you can't interpret that signal whatsoever. So by including a DC offset circuit, you can provide an accurate reference voltage, and as well you can basically position the waveform up and down on the patient monitor. It's very cool, nurses love it. It's great. All right, I would now like to pass it on to Jake.
So as Ashley described, what we're using to actually take the measurements is the Arduino Uno. So what the signal that comes from the output of Robin's offset circuit goes into the Arduino. It's reading those dies, converting it to a digital die, and sending it off to the Pi. It's also taking those dies, putting them into calculations, and sending it to the LCD screen that shows the heart rate and the map and that kind of stuff. So that's what that's doing. It's sending to the Pi, and the Pi is using what's called processing to convert that. So as you can see in the bottom corner there, that's what the Raspberry Pi looks like. It's about the size of the Arduino board, if you don't know what it is. It's a small PC, it's Linux-based. So what we're using is a program called processing. It writes the code that displays the waveform, as you'll see when they demonstrate it. And I think we're going to pass it back to Ashley and Reg. Nope, I'm looking at
We'll be demonstrating some of the bonus parts that we have added into our device.
So first off was the keypad, and as you can see on here, it's our third revision of our lead select. So 0 is not applicable, nothing will appear on there. First 3 leads are ECG, and 4, 5, and 6 are the simulator ECG, and then 7 will indicate the 1 millivolts pulse.
Next, we have the backup battery and battery alarm system. This allows our device to become mobile, and if anything does cause a power outage, it can run for a set amount of time. The alarm will also beep when the machine is turned on. It will also alarm if the battery is low, and has an automatic trickle charge above 10 volts to allow the battery to charge anytime it is plugged in. As I said, this is a very good clinical one, as you can easily move it anywhere it's needed. Now I'd like to invite Dan up to show the miscellaneous modifications.
We invite the judges up to see several aspects.
So you're not looking at that.
Oh man, that's really
the battery configuration as well as the AC power. The three relays, the solid state is from our power AC to ports, as well as the relay for the old battery. So, 2 telecom relays.
This year is a culmination of our 3 years here at Durham College, and there are a few people we'd like to especially say thank you to.
Okay, so obviously thank you to anybody who helped us out. Special thanks to Dave Kay, who has had to put up with us running up to his office countless number of times during the day, turning on PCB labs at all hours. Richard Tidman, obviously, is our professor who's led us through this whole entire project throughout the year. Pravin for our base understanding, along with Lauren for our lovely SIRE knowledge that we checked back on. Sandra for helping us with the presentation, other like clinical aspects of all this information that we had to reflect on. Louis for the overall power supply that we had to do within his class. A lot of that was the knowledge on building this, our circuit neatness, the motherboard, all that we got of Louis and how we want to have it done, so that played into it. Definitely big thanks to the Beaman team who lent us parts and knowledge throughout the year. I know we've been consulting everybody, so shout out to them. And the second years for an awesome job on what they did for us. They did everything we asked above and beyond our expectations, and we couldn't have asked for any more. So thank you to everybody, and thanks for listening. Yeah, any questions? That's fine. Okay.
When you were talking about the issues around the gate, and if you didn't build it properly, you could have unfaithful results. And I was going to ask you what those unfaithful results would be, what those unfaithful results look like.
Well, there could be any fluctuation in the actual signal itself, the waveform. You can cause a spike or a flat line somewhere due to the actual interaction with the circuit. Like, data that you're acquiring may not actually be representative of what you're showing.
And then in question 23, you talked about from a clinical perspective, what measurement represents the most critical piece of information to solid diastolic or mean pressure. And you were talking about the mean pressure, and I just wanted to ask what tissue perfusion is.
Tissue perfusion?
Yes.
Okay, so tissue perfusion is kind of a short definition. It's when all the tissues are getting adequate blood supply and oxygen supply. So your whole entire body needs obviously adequate tissue perfusion. You need to get oxygen blood to everything in order to make sure it still works. So as Jesse was highlighting with the map, that's the most vital information because it ensures, depending on what the pressure is, you have to have over 60 millimeters of mercury in order to make sure that your entire body is getting the right blood flow and everything's getting oxygen. Otherwise, you have your organs shut down, and obviously that is not good.
Thank you very much.
Again, Sandra, you good?
Yes, thank you very much.
Thank you.